Welcome again to the new lecture of solar photovoltaics principles, technologies and materials. We will just recap the last lecture's concept. Okay, so in the recap, what we did in the last lecture was we looked at the basic equations and assumptions in the quantitative treatment of p-n junction. So essentially we looked at the potential, electric field, how do you calculate them. So how do one thing you have to remember that electric field and potential both are continuous because the bands are continuous. So they are not discontinuous at the junction and the interfaces. So and from those and basic Poisson's equations, which is basically del dot D is equal to rho, we determined the electric field, then we determined the potential, and then we did the estimation of depletion region width. Okay. Depletion region width was equal to, W was equal to square root of 2 epsilon s VBI divided by Q into 1 over Na plus 1 over Nd. And this equation tells you very clearly that if your Na or Nd go up, the W goes down, which means in a p-n junction the depletion region becomes narrow. So this depletion region becomes, it shrinks. So this is W. Okay, it shrinks if the semiconductors are heavily doped, okay, or it expands when the semiconductors are lightly doped. It also tells in some sense, because we know that Wp Na is equal to Wn Nd. Nd. It also tells that if P side is heavily doped as compared to N side, the P side is more narrower, or if N side is more heavily doped as compared to P side, the N side is narrower as compared to the P side. Okay. So this is what the message of previous lecture is. So essentially, and so you can say the observations are one, built-in field potential is dropped more in the region which is doped lightly, and light doping will mean a wide depletion region. Okay. So let me see what we make out of it. So if you have a picture like this, let us say, so this is a p-n junction. Let us say somewhere here we have the depletion region. So this is P, this is N, this is the interface. So this is basically, you can say, capital W, all right. This is minus Wp and this is plus Wn. Okay. Now here we are saying that doping of P is similar to N. Okay. So they are not, generally if one is heavily doped we write it as P plus N, if N is heavily doped we write as Pn plus, if both are lightly doped we will write them as Pn junction. Okay. So if you now plot, let us say we want to plot electric, first we want to plot the carrier density. So when you plot the carrier density of this side is, so this is Nd and this is NA. Okay. If you want to plot now electric field, so this is carrier density rho. Now we want to plot electric field, okay, Ex. The electric field is 0 at interface and it is also 0 here. It changes the curvature at this point, the bands change the curvature at this point. So, as a result the electric field is 0 at that point. The variation is like this. The electric field varies, the rate of change of electric field is it's same in both the regions. So, this is minus xp, this is minus wp, this is plus wn. Okay. So, essentially both the regions have same width. As a result, the slope of electric field is also similar in both the regions. If you look at the potential, now let us look at the potential, the V, and let us say I can use slightly different color. Let us say we start from 0 here, this is 0. It achieves a value VBI in this region, okay. It has a 0 value here, it goes through a change like this in the, and this value being VBI, okay. Now it depends upon the reference, all right. So if reference is slightly above, if reference is closer to the central axis, so this is x, okay. It depends upon basically what is the reference for the energy levels, because V is nothing but minus E by Q, okay. So you have certain level, then it goes increases, potential increases at minus Wp, it starts increasing until you reach plus Wn, going through the I mean there is no origin of this, there is no meaning of this origin, but it is just the interface, okay. So now if you do a comparison with another semiconductor junction, which is, let us say P plus N in this case. So this is the interface, all right. So what will happen in this case is your depletion region will shrink on this side, it will remain wide on this side. So this will be minus Wp, this would be plus Wn. So this would be basically the negative carriers, negative fixed charges, this will be positive fixed charges. Similarly here we didn't draw them, okay. Now if you plot the charge density here, the charge density in this region is lower, but for longer distance, in this case it is higher, but for shorter distance. So this is Nd and this is Na, and basically we are saying here is the product of Nd into Wn is equal to product of Na into Wp. So you can see that if Na and Nd are not equal, Wp and Wn will also not be equal. Now if I plot the electric field in this case, the electric field goes like this, it is continuous, it is like this. This is what is, I can say, is the electric field, okay. Now if I look at the potential, this is x, the potential goes as this is some level 0. I can use a different color. So it goes as something like this. So this whole value is VBI, but it goes through few changes here. So the region which is lightly doped, the potential is generally dropped, so it doesn't go through 0 here. So the region which is lightly doped, the potential gets dropped a little bit more as compared to in the region which is heavily doped, and the profile changes a little bit in terms of, because of changes in the carrier density in the two regions. So it's always continuous, it's never discontinuous, but the profile changes to something like that. So you can see that the electric field goes from 0 to some value in the heavily doped region, whereas it goes over a shorter distance than it goes in this region. So you can see that the drop in the electric field is more in the region which is heavily doped, right, as compared to the region which is lightly doped, okay, because within that small distance you have large charge density, and suddenly you go to 0 charge density here. So you come from 0 to large charge density, which means you have larger gradient in the electric field as compared to in the region where you have a smaller charge density over long distance, and correspondingly you have variation in the potential. So this is how the variation of potential and electric field is going to happen. Now in most solar cells, how is it relevant to solar cells is, in most solar cells, at least crystalline silicon solar cells, the top layer, which is called as emitter layer, is more heavily doped than the bottom layer. As a result, depletion region lies mostly in the, where will it lie? In the bottom region. So this is how, so you have a solar cell like this. This is emitter and this is base, okay. This is heavily doped and this is lightly doped, right. So the depletion region basically extends up to a large distance here, but up to a very tiny distance in this region. So most of the depletion region lies in the base layer than in the top layer, okay, and emitter layer is also very thin, and we will discuss the reasons of that later, why is that in this fashion in the solar cells when we come to crystalline silicon solar cells, but this is how it is, the depletion region in the so you can say if your for example if your ND is much smaller than NA, then you can say that W is approximately equal to square root of 2 epsilon s VBI divided by Q into ND. It is solely governed by ND. So if there is a 2 order of magnitude difference in NA and ND, then obviously one is going to be ineffective. So as a result, ND is the more dominating factor over NA in determining the. So now we want to look at the effect of bias. Effect of bias means effect of applied field, okay. So what you do here is, essentially what you do is that if this is your PN junction, oops, it's a little bit. All right, and we said that this is VBI. What do you mean by bias here? So, bias in semiconductor PN junction, it's called as either forward bias or reverse bias. What does it mean? It means that you have a PN junction here. The P side is, so forward bias means your P side is made more positive, is connected to positive terminal, and N side is connected to a negative terminal. This is called as forward bias. What will happen in this case? In this case, what will happen is that since you are applying negative bias to this terminal, the N terminal, the electrons in this N side will feel a force to go to N side, P side. Similarly, when you positively bias the P side, the holes from the P side will be repelled towards the, so they will be forced to go towards the junction to the N side. So, you have electron migration from here to here, and you have holes migrating from here to here. What essentially it means is that the energy barrier on this side is lowered. So, when you apply a positive bias, the energy barrier gets modified to VBI minus VA. This is forward bias, and you will have large junction current. The electrons hopping from this side, holes going from this side, there is large current that flows across the junction. As a result, you have large current. What happens in reverse bias on the other hand is, in the reverse bias, if I depict reverse as blue, so reverse will mean you are connecting P side to a negative terminal and N side to a positive terminal, which means the holes are going to go to, so the holes will go to this side and electrons will go to this side, which means they are drawn away from the junction, which means there is no junction current which is going to flow. The electrons and holes going to go through and they are going to go recombine at some point, and in the circuit there is no current that is flowing from the through the junction. So, junction current is very small in the reverse bias. So, in the reverse bias, essentially what it means is that this barrier increases, essentially it becomes VBI plus VA. So, essentially when you, so if I want to depict it, if this is at V is equal to 0, in the forward bias case it will become like this. Sorry, it will become like this. Okay. So, the junction height has reduced in the forward bias case. Okay. So, this is VBI minus VA. All right. In case of reverse bias, what will happen is it will become more like this. So, essentially your junction has become VBI plus VA. So, this is reverse bias and this is, you can say, is forward bias. All right. So, essentially let us say we have applied potential VA. So, VA is the applied bias. So, VA value is positive when it is forward bias and it is negative when it is reverse bias. Okay. So, let us say if this happens, then we replace VBI by VBI minus VA. Okay. So, depending upon the sign of VA, it will become plus or minus. Okay. So, for N depletion region, this will become, so Wn will become, for N side, for x smaller than Wn, between 0 and Wn, Wn will become 2 epsilon s divided by q into VBI minus VA into Na divided by Na into Na plus Nd, sorry, it should be Nd to the power half. Vx will be Vbi minus Va into minus of Qnd divided by 2 epsilon s into Wn minus x to the power 2, okay, and Ex will be, so you are just replacing this, okay, so this will be Qnd divided by epsilon s into Wn minus x, okay. Electric field remain the same, it's only the bias which has changed, okay. Similarly, if you write the same equations for P side, for x less than 0 to minus Wp, your Wp will become equal to 2 epsilon s by q, sorry, did I have factor of half, yeah, into Vbi minus Va into Nd divided by Na into Na plus Nd, this to the power half. Vx will become Qna divided by 2 epsilon s into x plus Wp square, and Ex will become minus of Qna divided by epsilon s into xp plus Wp plus x, okay, and the junction width will become W will become 2 epsilon s divided by q into Vbi minus Va into Na plus Nd divided by NaNd, and this whole to the power half, okay. You can write this as 1 over Na plus 1 over Nd also, okay. So this is what the change in the bias. So you can see that as you increase your applied bias, junction width also, what will happen when you are in forward bias, the junction width, the depletion region width, so this should be the junction, it should be depletion region width, okay, actually to be correct. So the depletion region width will become narrower when you apply a forward bias, and when you apply negative bias, then this value will become larger. As a result, the junction width will become, or depletion region width will become larger as you apply more and more bias. And what happens here is then, so the effect that it has on the characteristics, IV characteristics, is like this, which we will derive. So when you draw the IV characteristics, essentially no current flows across the junction, it's a very small reverse current in the reverse bias. So this is reverse bias, so this is 0, okay. So when V is less than 0, it's reverse bias, very small current flows across the junction. As a result, what you have is very little current flowing. This is reverse bias, and then in the forward bias, because a large current flows through the junction by electrons pushing across from N to P side and holes pushing across from P to N side, where there is a very large junction current, and this current is essentially the forward current. So this is forward current, and mathematically speaking, this current is basically I is equal to I naught exponential of QVA divided by KT minus 1, okay. And this current, in the reverse bias, it is basically I is equal to I naught exponential. So you can see that this will be positive in this region and this will become negative in this region. So in a sense, sorry, I don't have to write this, but this VA will become, VA is negative in this region and VA is positive in this region, and this current is essentially equal to, we will continue this in the next lecture to work out the electrical characteristics of PN junction, okay. Thank you.